This is TechKnow, a show about innovations that can change lives.
The science of fighting a wildfire.
We're going to explore the intersection of hardware and humanity, and we're doing it in a unique way. This is a show about science by scientists. Let's check out our team of hardcore nerds as TechKnow goes on the road to Caltech in California. Dr. Crystal Dilworth is a molecular neuroscientist. Tonight, jellyfish. Why this creature from the sea can help us produce more efficient submarines and tell us about climate change. Dr. Shini Somara is a mechanical engineer. Tonight, from landslides to crystals in space, we're going to show you some of the most exciting research conducted in these Caltech labs.
What is most exciting about this experiment is actually recreating what happens in nature.
That may help us solve some of our most complex problems. And I'm Phil Torres, I'm an entomologist. Are trees, that's right, trees, actually responsible for smog? Tucked away in the historic town of Pasadena, the California Institute of Technology, known as Caltech, ranks amongst the top universities in the world for science and engineering. NASA's JPL was founded at Caltech in the 30s and now leads the way for robotic space exploration. In this edition of TechKnow on the Road, we take you inside Caltech to show you the future of scientific discovery. I'm Phil Torres, and I'm joined by Dr. Shini Somara and Dr. Crystal Dilworth. And Crystal, you know well, because you got your PhD here, that Caltech is a hotbed of scientific discoveries. They're happening every day. And today, we're lucky enough to meet some of those scientists.
Absolutely. There's so much amazing work that gets done here by some amazing people. And we Caltech nerds, you know, we kind of have a reputation. We get depicted a certain way on sitcoms and the like.
The Big Bang Theory TV show?
Yeah, exactly. And so I'm very excited to show you some of my favorite people that are doing some incredible science. And the first person that I want to share with you is a MacArthur Genius Award winner. Dr. John DeBerry is taking a really creative and innovative approach to alternative energy, global warming, and conservation.
Climate change is not some far-off problem in the future. It's happening now. It's causing hardship now. Climate change is real, and we have to act now.
The debate about whether climate change existed at all, I think, is now is falling to the background, and now people, I think, accept it's a reality. It is here. And so now it becomes a question of what do we do to combat it.
On the front lines of combating climate change is Caltech Aeronautic and Bioengineering Professor, Dr. John DeBerry. Searching for energy sustainability solutions, he's taking cues from some simple animals.
The name of the game here is how you generate energy and how you consume it. And in biological systems, whether it's a school of fish in the ocean, a flock of birds, or just a plant growing in a field, they've come across ways to very efficiently generate energy and to consume it efficiently as well. And so our goal is to use concepts from physics to extract how they do that and apply it to systems like wind energy and underwater vehicles.
The common wind turbines seen around the world producing energy are the large three-bladed propeller type. But Dr. DeBerry is rethinking their size, shape, and overall effectiveness.
The challenge you see in wind energy is that an individual wind turbine, although it might be very efficient, it creates a very choppy air behind it. One of the challenges we have in a wind farm then is how to arrange them so that they can deal with that turbulence.
For answers, Dr. DeBerry is looking underwater and taking a lesson from schools of fish.
And it occurred to us that it was a different solution than what you find in nature when these fish are schooling in the ocean. So as each one of those fish is flapping its tail, it's also creating this choppy wake behind it. They swim close together, but they arrange themselves in such a way that they're able to be more efficient in the group than they are by themselves. And so that's what we wanted to get after, was a design for a wind farm where the wind turbines were actually more effective in the group than they are by themselves.
Believe it or not, this is a research lab. It's here in the dusty, hot, and windy Antelope Valley, California, that scientists are able to test their latest hypotheses about the best way to harness energy from all this wind. Is it always this windy out here?
Actually, this isn't a windy day. It's still pretty calm for out here.
Caltech postdoctorate scholar Matthias Kinzel spends much of his time out here, studying different types of vertical wind turbines.
I can see 2 turbines behind you. Can you tell me a little bit about each one?
The smaller one that you see out there is a 1 kilowatt turbine, while the bigger one is a 2.5 kilowatt turbine. The smaller turbine, not surprisingly, would be more beneficial for smaller applications, while the bigger one produces more power but also needs more wind. So it's a bit of a trade-off, what kind of winds you have, how many turbines you want to supply at that position.
What are some of the advantages to the vertical axis turbines?
We can space them closer and therefore get more energy for a given area of land.
Back in Dr. DeBerry's lab on campus, he's studying another sea creature for clues on improving real-world energy efficiencies: jellyfish.
They're so simple to begin with, but these are actually the first animals to figure out how to swim in the ocean. They're about 500 million years old. And importantly, they're very efficient in how they use energy. We as engineers are interested in stealing those ideas and using them for different technologies that would then allow us to use less fuel, for example, in underwater vehicles.
What's the jellyfish's secret? Why are they so special?
It's something called a vortex ring that they create. It's not unlike the smoke ring you could make with a cigar, for example, but these animals, each time they contract their bodies and relax, they create one of these vortex rings and they push off of it to move through the water more effectively than we do normally with our steady jet propulsion that we use for underwater vehicles.
Who's interested in this type of research?
The U.S. Navy has been particularly interested in this technology for developing underwater vehicles that use less energy. This helps them reduce the costs of the various missions that they support, but it also enables some new missions that they can't do currently.
So these small, not-so-simple organisms are really connected to 2 major issues: climate change and sustainability and energy conservation.
That's right. It's a unique situation in which these animals both tell us a lot about the problem in terms of their increasing populations as the ocean changes in climate, and also providing us clues to the solution in terms of new technologies that can be more efficient in their use of energy.
Well, thank you, Crystal. That was fascinating stuff.
Anytime.
From research deep in the oceans to miles above the Earth, Caltech scientists work tirelessly on new discoveries. Joining us here is Gwen Owens, a PhD and MD candidate who has an experiment going on right now on the International Space Station above us. Welcome to the show, Gwen.
Thank you very much for having me.
So, Gwen, tell me about this disease that you're studying.
The disease my lab is studying is Huntington's disease, which is a neurodegenerative disorder. It's a disorder that affects the brain, and proteins build up that cause the brain to stop functioning correctly. And about 10 years after symptoms start, then patients actually die of the disease. There's no treatment and there's no cure for this disease either.
So how does space research come into your own research?
My lab is an X-ray crystallography lab, which means that we study the 3-dimensional structure of proteins. And to study the 3-dimensional structure, the best way we can get a picture of them is actually by getting a crystal of a protein. And we haven't ever been able to get a crystal of these proteins, this particular protein that causes Huntington's disease.
Is that why you're going into microgravity then?
There's been good evidence that protein crystals grow differently in microgravity than they do on Earth.
So you shot your research up on a rocket. Yes. And it arrived at the International Space Station. How did it get there?
So it got up to the International Space Station on SpaceX. There was a SpaceX 3, which is a commercial resupply mission of SpaceX that was carrying not only our experiments, but a number of other experiments up to the International Space Station in late April.
So what does your experiment actually look like?
This is an example of one of the devices that is similar to one that we sent up. This is the apparatus that our proteins are loaded into for the actual crystallization experiments. Once we have a whole series of these devices, we put them into a large metal box. And then they're put into an insulated, protective container that keeps it at a very precise temperature as well for our experiment.
So what are you waiting for? When do you get the results?
We'll get the results when SpaceX 4 comes back, sometime this fall.
Do you have any idea what to expect when the rocket comes back?
The best case scenario would be if we could get a crystal of the protein that's normal and the crystal of the protein that's also mutated. So we could see how the structure changes when a person gets Huntington's disease.
So if you get those results and you have an image of what this protein looks like, what do you do with that information?
When we get an image, a 3-dimensional image of the proteins, they're uploaded to a website that's called the Protein Data Bank. And that's openly accessible to anyone in the world so they can see exactly what the changes are in the protein. And we'd hope to collaborate with other labs who'd be able to work on drugs for this disease.
So the idea, the end goal of this is to create a medicine.
Yes.
So of course, when this thing comes back and visits us again here on Earth, we're definitely going to be checking in with you to see the results here on TechKnow.
I would love to come.
Shinny, we had the opportunity to meet some of the grad students here who are doing some really amazing work.
Yeah, I met two guys who are trying to understand exactly how water can shape landscapes.
And I got the opportunity to meet with one of the students here who is studying how smog forms. And it's a lot more complex and interesting than I originally thought. And being in LA, smog is kind of an issue. So let's take a look. The air pollution in Beijing, China today could be described as a nuclear winter. Health risks are severe, and with the smog blocking sunlight on a daily basis, plant seedlings struggle to grow. But in Los Angeles, air pollution is controlled better than it's been for decades because of strict government regulations. Regulations that are based on smog research done in labs like this one at Caltech.
I'm Kelvin Bates. I'm a second-year graduate student studying atmospheric chemistry here at Caltech.
What is your field of study, and what specifically are you working on?
Our big question, I would say, is how does smog form?
Part of the answer includes trees. Yes, trees. But don't blame them just yet.
Trees give off a bunch of different chemicals, obviously oxygen that's useful for us to breathe.
And a variety of other compounds, including isoprene.
We know that isoprene is one of the main chemicals that gets emitted by trees, and that it alone is responsible for a lot of the smog that we see.
Here's how it works. When isoprene mixes with man-made pollutants like car and power plant exhaust, that mixture forms ozone and other particles responsible for smog. Getting to the bottom of how that process works is what Kelvin is researching.
But we don't know exactly what pathways, what chemical reactions take place that convert isoprene to substances that are sticky enough, essentially, to help form those particles. And so those are the chemical reactions that I'm trying to figure out.
So this conversion from isoprene, which comes out of plants, to this oxidized sticky stuff into smog, that's what you're working on in this hood.
Exactly. So what I try to do here in the synthetic lab is make some of these chemicals very pure so that we can see exactly which chemicals are responsible for the smog. A lot of these chemicals haven't been made in the lab before, so we're trying a lot of new things.
Once the chemical is created under the hood, it gets tested in a different Caltech lab across campus.
So now we're down in the atmospheric labs where we bring the chemicals, once we've synthesized them, and we put them into our atmospheric chamber to see what happens to them in the environment. This is what we call the environmental chamber.
Wow.
It's basically just two big Teflon bags where we mimic what happens in the atmosphere. And so we inject the chemicals that we've synthesized into the bags, along with other chemicals that you'd probably find in, say, a forest or a city. And we use some instruments that we've developed here in this lab to see what happens to them in the atmosphere. You can see in there that it's surrounded by banks of UV lights, and that's to mimic sunlight. And we let the reactions that would happen in the atmosphere happen in here, only they happen a bit faster because we've surrounded it with so much light.
So this is basically the laboratory version of the air over Los Angeles.
Over Los Angeles, over the Great Smoky Mountains, wherever we want to replicate, we can do it in a much more controlled and pure fashion than we would get if we were just to test these things outside.
There's a lot going on inside the chamber, and all of that information comes here.
Exactly. This screen is showing us the data from last night's experiment. It's showing us the concentrations of chemicals that are important contributors to smog, like ozone and the nitrogen oxides that cars produce.
Now, what is the takeaway from this experiment?
That the particular chemical and the reaction pathway that we isolated last night isn't responsible for forming the ozone in smog.
And when you finished all your work here, what's in the future for you?
still not sure about that. I've got a good 3 years to go. I think it'd be great to stay in the academic realm and keep doing the kind of research that I'm doing now. I think it'd be really interesting to bring what I've learned about the science back into helping shape policies that can improve air quality in the US and around the world.
So Phil, just to clarify, we should not be cutting down trees, right?
Absolutely. You know, he was just showing how trees are part of this complex thing. And when human pollutants get into the air, it mixes with the trees and we get this smog. So it was a really fascinating study to look at.
So as graduate students here, we get to do a lot of really exciting theoretical research, but what's the next step for Kelvin?
I'm convinced this kid's gonna run the EPA someday. Shindy, you got to meet some of the researchers here who are studying mudslides in a laboratory.
Yeah, I got to meet two guys who are really gaining an understanding of the power of water and how that's shaping our landscapes. And they're literally creating nature in a lab. Let's take a look.
At Caltech, fourth-year graduate student Jeff Prancevic studies how rocks and gravel called grain in lab experiments interacts with water and gravity in nature.
So Jeff, can you talk me through the major components of this experiment?
We draw water from this tank using a pump to the top of the test section here, and then the water will run through the gravel and over the gravel and then spill back into this tank. So we just recirculate that water, and we can adjust the speed of the pump to adjust the discharge, the actual flow rate of water coming through the flume. We are trying to identify the conditions at which things will begin to move. Eventually, we'll increase the discharge a bit more, and that stress will be just enough to overcome the resisting stress that's derived from the friction of the grains. And this will initiate a failure, and the grains will begin to move down slope.
What is most exciting about this experiment is actually recreating what happens in nature.
That's the beauty of laboratory flume experiments, is that we can simplify things that are going on in the natural world and observe them in a controlled laboratory setting, and with the possibility of actually applying what we learn to these catastrophic debris flows that may damage infrastructure or take lives.
It's fascinating to simplify how water flows over sediment in order to really understand the science of landslides. But what happens when you make that experiment bigger and more powerful?
Laurent Jambert is a postdoctorate scholar at Caltech who's studying river dynamics.
What is your experiment similar to in the real world?
The size of the flume is about the same size as certain rivers in the real world. So we have the same grain types in there, we have the same discharges that we can reach in mountain rivers. We pretty much are in the same configuration as in the field.
Except for one high-tech addition, smart rocks.
So Florian, I find these incredibly cool. Smart rocks.
Yeah. So you have this piece inside, which is basically an accelerometer, and it records the acceleration of the grain. So we can tell when a grain is impacting another grain, we can tell the energy that is released during the impact.
So these are data collection points.
They are, yeah. They are labs in rocks.
So what kind of speed is this?
I think it's about 4 meters by second.
One data point goes in. Oh, wow.
The data recorded by the smart rocks helps to further understand exactly how the size, number, and speeds of other grains erode the land.
So what's the ultimate goal of your research?
It is to find a way to describe appropriately the physics that controls the erosion in a mountain range environment.
And to help scientists to better understand how our landscapes were formed and how we can better build around the forces of nature.
And joining us now is very special guest, Dr. Mike Brown. Dr. Brown is a professor of planetary astronomy, and while he's made many significant scientific discoveries, he's probably best known as the man who killed Pluto. Welcome to TechKnow, Dr. Brown. Why'd you do it?
You know, the obvious answer is that it really had it coming. If it wasn't me, somebody else was going to do it, and it just needed to happen.
Tell me the story.
The short version of the story is that Pluto never should have been called a planet in the first place. It was really just a big mistake, and there was a mistake just because everybody thought it was big when it was first discovered. They thought it was as big as Jupiter, and then realized it was smaller and smaller and smaller. And now it's known just how small it really is. It's smaller than our moon. And there are thousands of other things out there just like it.
So if Pluto isn't a planet, then what is it?
The official definition for what Pluto is a dwarf planet, which I like to think of as things that look like planets but aren't.
I love the story of the declassification of Pluto because I think it's a great example of how new information can really change the entire idea that a group of scientists have about something that they've taken for granted to be true for a really long time.
You came out with this announcement about Pluto. Did you face much resistance within your field or in the public?
I got hate mail from young children for many years. I don't get as much from young children because young children now think it's funny that they know Pluto's not a planet and their parents don't. I get obscene phone calls late at night. It's always on like a Friday or Saturday night, so I'm fairly sure it's the same children from whom I got the hate mail, and they're now off in college at their first frat party, and they think it'd be really funny to call me up and yell at me. So I save them all because they're hilarious. And there are definitely a very small number of scientists, but a very vocal set of scientists who don't like the idea, mainly because they study Pluto and they feel like saying it's not a planet means that it's less important. And I think that they are looking at things the wrong way. I think it's better to classify things correctly, sensibly, and then let's explain why Pluto's actually really quite important.
You also found the largest object in the solar system in the last 150 years. What was it?
So this is Eris. It was the object that led to all of this debate and eventual demotion of Pluto, and it's one of these objects out there in the Kuiper belt. It's very far away. It's about 3 times further away than Pluto is right now, but it comes in really close. It's tilted by about 45 degrees compared to the planets in the solar system. It's got a moon around it. It's got a surface covered in methane. It's got nitrogen in its atmosphere, but most of that atmosphere is frozen out on the surface because it's so far away. It's this fascinating little world. I don't think the fact that it's a dwarf planet makes it any less interesting.
It's really impossible to imagine that we're the only life form here on Earth. Do you ever think about discovering other life forms?
I think about the question a lot, and I don't even think the right question is, are there other life forms out there? Because the answer has to be yes. There's just no possible way that the universe could exist in such a way in its vastness that we are the only intelligent life form that develops. So that would be crazy. Now, the important question is it common or rare? And that's a really interesting question. Are there intelligent life forms at every star that we look up in the sky? Or we look up in the sky in our galaxy, we're the only ones, and you have to go to the next galaxy to find the other one. That's the sort of question that we have no idea what the answer to that is. And those are some profoundly interesting questions to ask. But places like Europa, if you find microbes under the ices of Europa, places like Titan, if you find things living in this weird exotic methane seas on Titan, that answers that question immediately. That tells you life is incredibly easy to form. If you give it the right conditions, you can't stop it from forming, and that'll be fascinating. Once we know those things, and we know that there are planets like the Earth, and I think we can answer that question in a really sensible way, like that there are life forms around, one every 100 stars, or every 10 stars, or every star. I think we'll know it.
Well, Dr. Brown, thank you so much for joining us. Thank you for killing Pluto. I think we all know now it deserved it, right?
Thank you. It was my pleasure.
And that wraps up a special episode of TechKnow on the road here at Caltech. Be sure to join us next time.
Dive deep into these stories and go behind the scenes at aljazeera.com/techknow. Follow our expert contributors on Twitter, Facebook, Google+, and more.